Hello, welcome to today's webinar, Measuring PNT Performance in Challenged Environments, brought to you by GPS World Magazine and our sponsor of the event, Orolia. Orolia is the world leader in resilient positioning, navigation, and timing solutions that improve the reliability, performance, and safety of critical, remote, and high-risk operations, even in GPS and GNSS denied environments. I'm Mackenzie Shoemaker, content marketing producer for GPS World, and I will be your moderator for today's event. Before we get started, I want to let you know that you are in a listen-only mode, and today's webinar will be recorded. A recording of this webinar will be posted to gpsworld.com/webinars and will also be emailed to you tomorrow. At this time, I'd like to acquaint you with the ways in which you can participate during today's presentation. Please notice the Q&A panel at the left-hand side of your console. If you have a question, type it in the panel's text box, then click Submit to place your question in queue. We encourage you to ask and enter any questions you may have for our speakers during the presentation. We will address these questions at the end of the presentation during the Q&A portion. Questions submitted during registration have already gone to our panelists and may be covered during the presentation. If you experience any technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issue, and assistant producer Aurora Harris or I will personally assist you. You may learn more about our speakers by viewing their photo, bio, and email address in the panel located on the upper left-hand side of the console. To the right of the console, you will find a PDF of today's presentation slides, which you can download, and a link to visit both the Orolia and GPS World websites. If you are logged into your social media accounts, you can share the webinar's title, description, and URL with your friends or colleagues using the Share This widget you'll see at the bottom right corner of your screen. Now I'd like to introduce today's speakers. First, we will be hearing from Mitch Narins, Principal Consultant and Owner for Strategic Synergies, LLC. Throughout his career, Mitch has provided exceptional systems engineering and program management knowledge and expertise through his leadership of multi-organizational cross-functional teams in support of diverse and demanding civil and military customers. We will also be hearing from Jonathan Taylor, Lead Navigation Engineer for Orolia Defense and Security. Jonathan oversees and works on the development of the Flex Fusion engine, which powers the Versa PNT, providing resilient PNT solutions through satellite, inertial, and other sensors. Finally, we will be hearing from Zak Kassas, Associate Professor of Mechanical and Aerospace Engineering at the University of California, Irvine. Zak is also Director of the U.S. Department of Transportation Center, Carmen, focusing on navigation, resiliency, and security of highly automated transportation systems. At this time, I will be passing it off to Mitch Narins, Principal Consultant and Owner for Strategic Synergies, LLC. Mitch, take it away.
Well, thank you, Mackenzie. I guess we'll move to the first slide. Good evening, good morning, good afternoon to all of you. Thanks for joining. I'm going to talk today about the need to implement resilient time and frequency services. This is really a call to action and hopefully a starting point for a conversation that really needs to happen. My main point here is we've got to stop admiring the problem of GNSS vulnerability, and we need to do something about it. And that's what I'm talking about today. John Kennedy said, "We're not here to curse the darkness, but to light the candle that can guide us through the darkness to a safe and sane future." I like that quote, but I also say that hope is not a strategy, and we've been hoping for a GNSS resilient solution for many, many years. Interesting. So the bottom line up front, what do we need to do now, and what should we do in the future? Well, the most demanding user and sector needs are known. The levels of risks are known. The levels of threats are known. The need for resilience and flexibility is known. We know that there are mature solutions out there available, and implementation can begin immediately. We know that the threat is going to change. It's going to expand. There'll be new threats. But there really is no justification for waiting any longer. I had an old boss at the Pentagon who said, "Better is the enemy of good enough." From a PNT system engineering perspective, we start with need. So if there's a mission statement for PNT resilient services, I would say it needs to be to identify and implement solutions that will mitigate the impacts of GNSS interference, both jamming and spoofing. And we know that one size doesn't fit all, not for position, not for navigation or time, and partial credit is available. We should also always think about a disparate system of systems approach, because we're not looking for common mode failures. One GNSS system is great. Two GNSS systems does not make for resilience. The good news is that we've done an outstanding job in identifying the problems and potential solutions. But the bad news is that over the last 25 years, we continue to admire the problem rather than to implement and evolve these solutions. How significant are the impacts? I stole this slide from Todd Humphreys. This is just some of the numbers that came out in some studies about what the impact of losing GNSS services is. It's huge, we know that. I like to take a system engineering approach. Needs drive requirements, drive solution developments, which drive budgets, and then budget supports solution implementations, which are the goals. It seems for years, budgets are the ones who are doing the driving. It doesn't seem right. Solutions can be incremental, but the longer you wait, the harder it gets. Build a little, test a little, implement a little, repeat, repeat, repeat. Another John Kennedy quote I like is, there are risks and costs to action, but they are far less than the long-term risks of comfortable inaction. And we have been comfortably inactive for many, many years. We've studied the problem for over 20 years. Executive branches have provided guidance multiple times. So what's the problem? Well, it depends on who you ask. From a risk standpoint, we know that risk is evaluated by the severity of the impact and the probability of its occurrence. And that risk can be avoided, mitigated, transferred, or accepted. And we all agree that the impacts of GNSS interference are high. But for some reason, people have gone under the impression that the probability of a GNSS interference event is low. And we know that's not the case. It's happening all over the world. So therefore, people have assessed this as low and accepted the risk. Today's guidance must be that the probability of the occurrence of a GNSS interference event is 1.0. In other words, it's not if it's going to happen, it's when it's going to happen. And therefore, we have to consider the risk high and do something about it. Other impediments to solutions? Well, some people like to focus on favorite solutions. And for years, a lot of my friends in the GNSS community, and I do call them friends, have talked about more satellites and more signals and more antennas and more algorithms. Others have been trying to establish their own GNSS systems. And I can remember a full decade in Europe where talking about GNSS interference was a forbidden subject, because you can't ask for billions of euros for a new GNSS system at the same time that you're saying, and oh, by the way, it's not going to be good enough. I need to handle its vulnerabilities. Most users don't need centimeters, nanoseconds, or 7/9 of integrity. One size does not fit all. I don't need a solution that fits everyone's needs, but I need a solution that keeps everybody safe and secure. And some have treated a GNSS interference event as a force majeure. Some would call that an act of God. And therefore, if it happens, it's not my fault because I couldn't do anything about it. We know that's not the case. A GNSS interference event is something that is going to happen and that we need to do something about it. There's also the tragedy of the commons. Brad Parkinson likes to use that expression. Everyone knows how valuable GNSS PNT services are, and everyone knows that GNSS PNT services are vulnerable. But everyone seems to expect someone else will do something about it. They hope that somebody will take care of it. Well, hope is not a strategy. And what I've seen that many civil departments and agencies and governments around the world have been chilled to inaction because of budgetary constraints, where people in budget offices have said, if you want it, you're going to own it, and we're going to take it out of your own budget. So there's been this fear to accept the responsibility. And this has impeded and still impedes much needed real-world progress. This has been going on for over 20 years. One would expect multiple iterations of resilient solutions to have emerged and to migrated to face current threats. And they haven't. Budgets need to support mission needs. And again, better is the enemy of good enough. So let's take a little walk down the road from whence we come. So here's US policy 1996 to 2021, 25 years of policy about GNSS, interference, and resilience. So back in 1996, there was Executive Order 13010, and it recommended, through a President's Commission that they put up, to fully evaluate the actual and potential sources of interference and vulnerabilities of GPS, to sponsor independent integrated assessment of the risks to civil users, and to base decisions on the proper federal navigation systems mix, a systems of systems approach. And in 1998, the White House issued Presidential Decision Directive 63 on critical infrastructure. PDD 63 said, take all necessary measures to swiftly eliminate any significant vulnerabilities to both physical and cyber attacks on our critical infrastructures, including especially our cyber systems. It sort of made me laugh because I thought of those old Ten Commandments movies, the original one, Cecil B. DeMille, where the Pharaoh says something and the scribe says, so let it be written, so let it be done. Well, we've been writing this for 25 years, but so far nobody seems to have done it. Well, one thing that was done, and I take pride in this, is that in the Department of Transportation, we actually did something. And the Secretary of Transportation was directed to undertake a thorough evaluation of the vulnerability of the national transportation infrastructure that relies on GPS. And in 2001, the Volpe GPS vulnerability study came up. I was happy to say I was a part of that. And that landmark report came out in August 2001. It was actually released to the public on September 10th, 2001, the day before 9/11. That was 20 years ago. And one of its key findings is, and you could read this in the newspaper today, the GPS signal is subject to degradation and loss through attacks by hostile interests. Potential attacks cover the range from jamming and spoofing of GPS signals to disruption of GPS ground stations and satellites. Talk about a report that was before its time. It also said there's a growing awareness within the transportation community that the safety and economic risks associated with loss or degradation of GPS signal have been underestimated. We need to conduct comprehensive analysis of GPS backup navigation timing options. And the GPS signal system cannot serve as the sole source for position location. Public policy must ensure that safety is maintained. It said, in terms of time and frequency, it is clear that some form of backup to GPS timing is required. And backups for position and precision timing are necessary for applications involving potential for life-threatening situations. I also sort of laugh when I see it said that precision timing backups include cesium clocks or Loran-C for long-term equivalent performance, or rubidium or quartz clocks. We'll get back to that. But let's digress a bit and do a little bit of system engineering. So for resilient time and frequency, who needs what? What are the requirements? What solutions are available now? And what should we do now and in the future? And in terms of requirements, I'm talking about accuracy, availability, integrity, continuity, and/or coverage. Well, here are the 16 critical infrastructure sectors that the Department of Homeland Security have defined. But I want to point out there are two foundational utility services here, the communications sector and the energy sector. And though every one of these 16 sectors uses GPS timing, every one of these sectors also leans on the communications sector and the energy sector in order to exist. And I would call those the super utilities or the foundational utility services. And it is absolutely essential that the communications and energy sectors remain resilient. How resilient? Well, this is just a time chart. It shows essentially that different parts of the critical infrastructure need anything from a second to 30 nanoseconds. So again, one size does not fit all, but everyone needs time and frequency. The sources of time and frequency, well, we all know GPS and now GNSS. WWVB in the US is broadcasting. You've got network time protocol for internet time. You have precise time protocol, IEEE 1588, which is available primarily in local networks, but now they're trying to expand it over larger networks. You've got cesium clocks and rubidium clocks, and there's the timeline, if you will, on the bottom showing where they line up. Going back to 2004, of course, we had Loran-C and we had E-Loran coming out, and we talked about a future high-power, low-frequency ground wave, and that's where these systems sort of aligned. Back in 2003, Ron Beard, God bless him, from Naval Research Labs, put up this chart at a CGSIC meeting showing time and frequency sources. And that was pretty good for 2003. So I updated Ron's chart, and this is what it sort of looks like today. There's not just GPS, we have multiple GNSSs. We have LEOs. We have ground-based systems coming out. We have GEOs either existing today or in development. It shows that we don't have Loran-C with the X, but Loran-C is actually still available in the United Kingdom, Russia, China, Saudi Arabia, Iran, and South Korea. Interesting. This is what the US Loran system looked like back in 2008. And these are just 500 nautical mile footprints around the Loran sites. So forgetting about geometry or anything, you could essentially get 100 nanoseconds at anywhere inside any of these circles. And this is what it looks like today. For my friends in Europe, this is what the Loran system looked like in 2008. And this is what it looks like today. And in terms of the worldwide coverage, you notice that Russia maintains their east and west coast Chika chains. The Saudis maintain their Loran system, their E-Loran system. The South Koreans are building out their E-Loran system. The Chinese have had a Loran system for many years, and they announced that they're expanding it to the west. So it'd be interesting to ask, what do they know that we don't know? But let's get back to the timeline. Maybe we can see a way to stop cursing the darkness and light some candles. Executive Order 13905 came out last year, and it acknowledged the increasing growing critical infrastructure risk because of GPS GNSS. It acknowledged that the disruption could adversely affect national economic security, and it defined responsible use of PNT services, the deliberate, risk-informed use, including acquisition, integration, deployment, such that the disruption or manipulation of PNT services minimally affects national security, economy, public health, critical functions. But maybe most importantly, it said that we, the US government, should be putting language into the acquisition regulations such that if the federal government is buying PNT services, then these will be resilient PNT services. And that's really a good way of implementing it. Space Policy Directive 7 came out this year. It said to protect the use of GPS in federal augmentations, but it also said to incorporate the principles of Executive Order 13905. It also talked about implementing federal and to facilitate state, local, and commercial capabilities to monitor, identify, locate, and attribute space-based PNT service disruption and manipulations. The DOT Volpe Complementary PNT report came out, and that was absolutely a great document. And here are some words that were said by the then Deputy Assistant Secretary for Research and Technology. There are suitable, mature, and commercially available technologies to back up or to complement the timing services provided by GPS. but none of the systems alone can universally back up the positioning and navigation capabilities. This necessitates a diverse universe of positioning and navigation technologies. I call that a systems of systems approach, and it appears that all the ingredients are available. FAA Order 1770-68 also came out last year, and it talked specifically about the selection and use of time and frequency sources, and said that FAA program offices, system services, and application owners should migrate their systems away from using GPS as the sole or primary means for time and frequency. It essentially endorsed what NIST calls the flip, where instead of using a GPS receiver as your primary source of time and thinking of your oscillators as your holdover, you should think of your oscillators as your primary, and then you can discipline them, whether you use GPS or GNSS or some other signal from space or the ground. But the point is, you're not relying on GPS as the sole or primary means. Few words about risk. I sort of like the quote from Thomas Edison, "I've not failed, I've discovered 10,000 ways it doesn't work." And General Hyten recently said, "Failing fast and moving fast is how you learn." But somehow we've decided that failure is bad. We won't test until we're highly confident it'll work. And we're going to study it to death before we move on again. Somehow I feel that that denotes what we've been doing with GNSS vulnerability issues. So we know what the performance needs are. We know what the current threats and risks are. We know there's a need for resilience and flexibility, and we know that resilient solutions are available. So what are we waiting for? Again, here's the bottom line at the bottom now. We have this mission to identify and implement solutions. We know the needs, we know the risks, we know the needs for resilience, we know that there's mature solutions. There's simply no justification for waiting any longer, and there's certainly no plausible deniability. Recently, Dana Goward from the Resilient Navigation and Time Foundation interviewed Lord West. And Lord West, talking about the European Space Agency's Marinav study, said they seem to understand that satellites are not the be-all and end-all. And Dana said, well, essentially, what's standing in the way of them doing something? And Lord West sort of opined that the population as a whole doesn't seem to understand this whole thing about GNSS vulnerability, and that the people who are senior enough to drive solutions have so many other issues that they think are more urgent. And Dana asked, I wonder what it will take to make it seem urgent enough. And Lord West said, let's hope the wake-up call is something short of a national disaster. And I certainly echo his thoughts. So there are risks and costs to action, but they are far less than the long-term risks of comfortable inaction. It's time we stop admiring the problem of GNSS interference, GNSS vulnerability, and do something about it. Hope is not a strategy. So let's stop cursing the darkness and light some candles together before we get to a situation where we wish we had. And that's the end of my presentation. I'm going to hand it off to Jonathan Taylor. Jonathan, you there?
I'm here, thanks. So yeah, now that we've heard a lot about what the problems are and how we need to move forward, I'd like to talk a little bit about the practicalities of actually measuring PNT performance when we are in challenged environments. So this is about what we actually do at Orolia Defense and Security. So I'm going to start off talking about positioning versus navigation. Obviously, we're missing timing in here as well, but this presentation is mostly going to be about the positioning piece. But since that plays into navigation, I want to spend just a minute talking about the difference between the two. So positioning is where am I now, and lots of times where have I been, versus navigation is, well, it's both where am I going to, is that changing, what's my objective, what's in the way, what are the different ways to get there, what's keeping me from getting there, how fast can I go, which directions can I turn, and ultimately it's the ability to get from point A to point B or from point A to achieve an objective. So when you're measuring navigation, you kind of have to look at it as a system of systems. There's a whole lot of different components that come into play, just like all the things that I mentioned. But then, when you want to look at the system as a whole, you kind of have to look at other metrics. Yes, your velocity or your turn rates can maybe be performing well, but what about bigger things when you start talking about autonomy? You might want to look at, well, how accurately did I follow the road, or what were the number of accidents, or how many potential failures were there, and how bad would those have been? Would it have caused loss of life or critical mission failure? And most of all, when you're doing navigation stuff, you've got to have a really good understanding of, well, where are you developing and testing this stuff versus where is it actually being used? There's a big difference, say, if somebody's making an autonomous vehicle, testing it at some sort of test field and developing it there or on a computer simulation versus when you actually put it into use and get out on the streets. The stakes are a lot bigger, and there's a lot of other stuff, a lot of other environmental noise that maybe you're just not considering. But positioning is a key part of that navigation piece. And so how do we actually test this stuff? So the best case in how you're going to test your PNT performance is in the real world. We go to an event with the Army Futures Command called PNTAX, and there we have real live sky stuff going on. We're getting real messages from satellites. We're getting real threats that are there, whether it's jamming or spoofing or whatever other kind of attack. But the problem with this is that it's pretty expensive. You got to send people down there. They've got to put the event on. If you wanted to do some sort of real world testing on your own, there's a lot of approval, right? Because now you're jamming signals all over the place. There's a lot of red tape to go through that, as well as, all right, you did it last week. Well, what if you want to do it next week? What if you need to test again? And so you're limited in the time and repeatability on those. So if it's hard to test in the real world, well, what can you do? So at ODS, we've actually got two ways that we do a lot of testing when we're not at events like PNTAX. The first is we look at simulated threats with a live sky situation. So we've got a van that we've got a whole bunch of our Versa PNT units that you can see down on the bottom left. And we've got a lot of antennas to hook up to different receivers that may be in those. And then for the jamming and spoofing piece, we actually take a BroadSim, which is another Orolia product where we can simulate jamming and spoofing signals, and we inject those right into the receivers. So it's getting both the live sky antenna and the jamming or spoofing signals. If we wanted to look at a full doomsday blackout scenario, we've just got a signal attenuator, so we can just pull the switch on all that. We've also got a truth system. So we've got a dual antenna also using RTK, so we've got a really good reference that we're not jamming or spoofing that we can compare to. And when we actually are ready to test, we record all that data and we can play it back later. We can run it through the algorithms again. We've got the recorded IMU data. We've got the recorded GPS messages or whatever constellation we're talking about. And we can actually play that through the algorithms themselves later on. Another alternative that we've been exploring and developing is just a complete hardware-in-the-loop desktop simulation where we use a BroadSim Solo, which you can see down there on the bottom right, and we hook that into a Versa PNT. So we're not looking at live sky, we're looking at just simulated GNSS signals, and we simulate the IMU piece. We kind of bypass the actual IMU in the unit and inject simulated IMU measurements that are developed through a plugin. And a big advantage of that is that we actually know the truth, down to the millimeter, because it's modeled, it's a simulation. And the advantage to doing this for testing and development is that we've got perfect repetition. We can, go back to the exact same time and have the exact same satellites, the exact same profile IMU stuff going on. We've got complete control over everything. So, there we go. So when we do these tests, whether it's in the van or on the desktop, let's talk about testing a little bit. So we consider two major types of scenarios. We look at either straight routes or highway, because that's about as straight as we can get, where we'll drive for anywhere from 5 minutes to an hour, just on as straight a patch of highway as we can find, or what we'll call city driving, which is extremely dynamic, right? There's a lot of turns, a lot of stops, a lot of differences in speed going on. So it's important to look across multiple use cases and vehicle dynamics when you're testing. When we look at challenges, we'll look at jamming and spoofing. We'll look at different modularity types of those signals. We'll look at how long did it last, what was the power, how often does it happen. We can look at timing attacks through BroadSim. So it's important to have your scenarios defined and make them as repeatable as possible. Although also, when you're in the city, sometimes there's traffic going on. But you do the best you can. And we've also got multiple units that we test at the same time. So there's some repeatability built into that. So now when we look at metrics, right? So you measure stuff to get metrics. So one of the most important things is the ground truth, like I mentioned before. You've got to have something that's as good or ideally an order of magnitude better than what you're trying to actually measure the performance of. Some other metrics that often get overlooked is more of the qualitative things. So things like, what's your overall swap C, right? If you're trying to buy a lot of these to put in different vehicles, you need to know. You need to look at things like, what's your data output rate? What's the output format? What kind of values is it giving out? Is it just position, or is it giving me covariance and uncertainty values? What sort of sensors can it utilize? Is it compatible with these different outputs through a CAN bus or through different things? So a lot of those qualitative measures are pretty important. But then some of the, I think a lot of people in the audience are pretty technical. So, what are the metrics that I like to look at when I'm measuring performance of our Versa PNT or of any other system? So, this is just off the top of the list, but I want to look at what's my absolute position and velocity error, both in 3-dimensional and in the horizontal vertical. What's my confidence? And not just what's the 1 sigma level for the covariance, but what's the 95%, both for the ellipsoid or a circular area of probability, or even just the linear around different axes. Relative position and velocity error is something that I don't see get a whole lot of love. But I like to measure this as the Mahalanobis distance, meaning how many standard deviations is my estimated position from the truth. I might be, quantitatively 10 meters off, but if my standard deviation is, 5 meters in that direction, well, I'm 2 standard deviations off. So it kind of lets you know how good your estimate is relative to your uncertainty. What's the percent containment of truth? If I say that this is my 95% confidence area, how often am I in that? Should be pretty close to 95%, or else some math is going wrong. The position error growth rate, so you could look at the percentage of distance traveled, or the error is a percentage of distance traveled. You can also look at, if you're going on a straight line and you lose all your signals, how much is that drift and how fast does it grow? Can you model that as an exponential? And if you can, how does that exponential parameter compare to other systems when they drift? Attitude and course error. And then really importantly is, what's your convergence and reconvergence time? How long does it take you from a cold start to actually get a good solution? And then when you lose signals and you get them back, how long does it take you to continue getting that? Or if you've got a big turn or something, how long does it take you to get back on track? Related to that is signal acquisition or reacquisition time. I'm not really a signals guy, I'm more of a Kalman filter kind of guy. But we also have to look at things of, well, how well are our antennas doing? What's the signal loss at different strength levels and different modulations? What's the timing pulse errors? We've got to look a lot at that because position and timing are pretty key, or pretty intertwined together. And then lastly, in terms of metrics, what's going on inside your hardware? Is your CPU getting jammed up and maybe that's causing errors? What's your temperature like? If you've got oscillators inside, you want to measure how those things are doing. What about the receiver activity and which sensors are used in your solution? You might have 5 or 6 different sensors, but your algorithms may be only using 2 of them at a time. It's good to know what's getting used and what maybe you could utilize more. So when you're looking at all these metrics, it's really easy to want just certain numbers and to pick certain things out, like what's the root mean square error? And that's great. Metrics of a single value are fine, but it's really important to get the whole story, right? So I really recommend having analysts look over all the metrics that you can. So for instance, let's say that this graph is a measure of uncertainty, right? And you've got a requirement at this red dotted line that your circular area of probability or in your uncertainty has got to be under this red line. Well, if you just look at when you get, say this is 1 second updates, or you only update it when you get a GPS measurement. Well, what about when you have outages? What about all the time, right? If there's a second in between 2 of these dots, well, in your system going at 100 or 1,000 hertz, what about all the time in between that? Well, if you're familiar with Kalman filters, you know that things actually grow over time. So, in between, say, the second and the third dot or any of the other ones, your uncertainty might actually be growing in between those updates above what your threshold is. And so, you really got to report that because those uncertainties are going out to the data consumer. You can't just pick and choose, at certain times. You've really got to look at the full story using adequate sampling rates for all your measurements. So when we look at all the data together, like I said, it's easy to give your error bounds and it's easy to talk about just, singular metric values, but it's really important to look at the whole story, look at a whole lot of graphs, because it's hard. You've got a whole bunch of different things that you're considering. What was I turning here? Was there an outage? How strong was the jamming during this? What was my velocity? What was my accuracy going in to the turn versus going out of it? So you really need to look at a big, long story to figure out how things are going. And just as an example of a piece of the story that we would look at, so if you look at the top right here, this is the number of satellite vehicles that we could see during a jamming power ramp scenario. So we start off doing pretty good, and then you can see the number of satellite vehicles drops down right around 2000 hours, a little bit before that. And then if you go over to the top left corner, you can see the position error starts to grow about the same time that we start getting less satellite vehicles. In the middle top, we've got our yaw and our yaw or heading error. And, it tells kind of the same story. The bottom left is just an overall position graph where the blue dotted line is the true GPS or what the receiver thought the position was. The red is the actual truth. And then the black is kind of our drift. And, so you can see during this, we still got the turns, but our IMU started drifting a little bit. And one of the things that I think is the most important is down on the bottom right. That's actually the uncertainty graph. So that's, 1 or 2 sigmas, depending on the graph that we're looking at, in each of the 3 directions. So you can see the X and the Y are definitely a lot higher than the Z uncertainty, which is to be expected when you're drifting and going through turns. But it's really important to know, if I wanted to draw a circle about how sure am I that I'm in this position, that uncertainty is really the biggest piece. So you can see, right, I'm looking at, well, when did we actually turn and how far off were we? What was the overall distance error? What were the environmental and situational things going on when we had that error? And, we can dig into this as far as you absolutely want. So where are things headed with metrics and measuring things? So one thing that we're trying to do is look at better hybrid simulations, meaning in the long term, we want to be able to take that broad sim with the hardware in the loop and do really good IMU modeling. So add in different noise models for different road conditions and stuff like that, so that we only need to ever drive the van just to prove to ourselves that the algorithm, actually does what it's doing on the desktop. We could develop everything right there in the office if we've got really good IMU models. In the short term, when we're trying to get metrics and do development, we're already doing the hardware in the loop testing. We're currently working on being able to bypass the physical IMU and replay the IMU values so that we can have just the live sky and the threats from the broad sim. We can have the real IMU measurements coming in, since we haven't modeled them just yet. And what this does is it allows for a whole lot of iteration when we're doing development, right? We can run scenarios, we can get metrics, we can make tweaks, and we can just iterate that, rinse, lather, and repeat over and over and over, really with the metrics driving the development the whole time. And the whole idea of that is so that we develop using our simulation or emulation, we test it in the van, and we confirm it at those live sky events like Pentax. So that way, somebody decides to buy a unit, boom, we've developed it, we've tested it, we confirmed it, and now if somebody's life is going to depend on that, there's not going to be any surprises. One last benefit to doing this is it also allows a really cheap way. If we wanted to develop something for, space applications, well, we've got a simulator. We don't have to send something up into space to test it. And that's all for me. Thank you for your time, and I'm going to hand it over to Zach now.
All right. So thank you, Jonathan, for an excellent presentation, and thank you, Mitch, as well. It's a pleasure to be with everyone here. Good morning, good afternoon, or good evening, depending where you are joining us. I see people from around the world, which is exciting. So what I'm hoping to show you today is that if you don't have GPS, that's not necessarily a problem, as a lot of people think, because the truth is out there. So let's see what I mean by that. But before starting my presentation, I would like to thank former and current students in my lab who contributed one way or another for the great work that you will be seeing here. I appreciate their hard work. So as I alluded to earlier, the truth is out there. The signals are out there. So GPS or GNSS not being available is not necessarily the end of the world. In fact, it's the beginning of a new world. It's a beautiful world, the world of signals of opportunity. A lot of you are familiar with those signals. These are signals that are not intended for PNT. They can be coming from terrestrial transmitters like AM/FM radio, cellular with all its generations, 3G, 4G, 5G, digital television, or coming from space like Iridium, Orbcom, or more recently Starlink and other mega constellation low Earth orbit satellites. Now, these signals are very powerful. They are very useful for complementing GPS or GNSS, or even replacing them altogether. So what I will show you next is a series of experiments that we had achieved in my lab. And they are based on something we called Matrix. This is a cognitive software-defined radio. It stands for Multi-Channel Adaptive Transceiver Information Extractor. Matrix can produce a navigation solution in a standalone fashion from different signals of opportunity, from different cellular signals, CDMA, 3G, 4G LTE, and more recently 5G. It could also produce navigation observables and a navigation solution from LEO satellites, Orbcom, Globalstar, Iridium, Starlink. You can fuse it with external sensors like IMUs and LiDAR, and you can even fuse it with GNSS receivers. So let me show you some exciting work we had achieved with Matrix. The first one is navigation of UAVs, of unmanned aerial vehicles, with cellular signals of opportunity. So let me go to the first video, and I will speak over as you see the video running. Okay, so what you are, just if I can get a confirmation from someone that the video is displayed properly. Looks like we have a technical hiccup. Okay, so for some reason I cannot see the video. I apologize for this. Okay, I think the video restarted. Okay, so let me speak over as you see. So what you are seeing here are my students setting up the video, the UAV for flight. We had equipped this UAV with a matrix to listen to cellular LTE towers in the environment. And what you are seeing here in the top right are 11 LTE towers, some of which are several miles away from where we were flying. We were listening to signals from these towers, and we are producing carrier phase measurements that we are feeding to an estimator, to an extended Kalman filter that will estimate the UAV's position, velocity, and time. What you're seeing in blue is the ground truth. This is from a GNSS RTK solution, a GNSS RTK system with an IMU, with a tactical grade IMU, and we also have RTK for GNSS there. So this is a sub-meter accurate ground truth. What you're seeing in red, this is the solution we are producing only with LTE signals and an altimeter. So as you see here, we flew more than 600 meters, and the 2D and 3D position root mean squared error was less than a meter. So you actually can get less than 1 meter navigation accuracy with cellular LTE towers on a UAV. So the next question that we answered was, well, can you get this done on a high altitude aircraft? So to do this, we collaborated with colleagues from Edwards Air Force Base to test out our receivers and our navigation algorithms on Air Force aircraft. So we demonstrated that you can actually fly a high altitude aircraft, and we can, you see here, this is the badge that the pilots wore. It's called Sniffer. You see here, this is the aircraft that we flew. It's a C-12. This is the RF rack. Those are some of the antennas that we retrofitted the aircraft with. Those are some of the pilots that flew the aircraft. We are very appreciative of their help in this mission. This is some footage from the control room. And now what you will see is the aircraft flying and listening to cellular towers, 3G and 4G towers in the environment. What was fascinating is that we were able to, by the way, this is just us mapping those towers as we fly. You see, just we pinpointed a tower, we estimated where it is, and we will start using its signals. What was fascinating is we managed to track these signals at altitudes as high as 23,000 feet. We didn't fly over 23,000 feet for FAA regulation purposes, but those signals were available up there. We tracked them and we produced a navigation solution with them. We also listened to towers that are more than 100 kilometers away. So those signals are very clean up there and are useful for aircraft navigation. What you are seeing in blue, this is the ground truth of the aircraft from its onboard navigation system, which uses GNSS and an INS. Whereas in green, this is our solution. This is what we call radio SLAM, radio simultaneous localization and mapping. No GPS or no GNSS signals at all involved in this solution. The only thing we used was the altimeter measurement from the aircraft. This is actually a fun thing that the Air Force pilots did. They landed on the runway, and you see our solution exactly landing with the aircraft, and they took off again. So a touch and go, and we were all along, 60 kilometers of distance traveled, and our position root mean squared error was less than 5 meters, only with cellular 3G and 4G signals. So the next question that comes to mind is, well, can you really do this in a real world GPS jammed environment? So what I had shown you is the signals are there, right? GPS is not jammed, and we are fictitiously cutting GPS from our navigation filter, and then trying to see, can we actually estimate our position, velocity, and time just using the cellular signals of opportunity. So for some reason, the video doesn't seem to be playing, at least on my side. Let me try to replay it again. Okay. So this is a video of experiments that we conducted at Edwards Air Force Base about a couple years ago during experiments that they conduct there. They call them NavFest, Navigation Festival, where they do jam GPS over a period of about 2 weeks in the Mojave Desert. So this is us driving just before sunset to the base. You see here footage, really, we are in the middle of nowhere in the Mojave Desert. The idea is we will try to navigate using signals of opportunity from a tower that is on base, that is experiencing GPS jamming. Nevertheless, we will try to use its signals to navigate a ground vehicle and see how well we can do. So you are seeing here, this is the vehicle. You are seeing our control room, so to speak, which is basically a room in a small motel in the area. So this is the vehicle that we drove. We equipped it with GNSS antennas, with a Septentrio device that basically has GNSS RTK and a low-end tactical grade IMU. You see here all the antennas and all the different RF front ends that we use for data collection. Then you see here matrix. We only used the cellular 4G for this particular experiment, the LTE part. And you see here some pictures of the interface that Matrix has. You can set up your, if you've used GPS receivers before and interacted with them, it looks pretty much like a GPS receiver where you can set up your settings, you can see your correlations, you can see your pseudo range, you can see acquisition, and you can tap into different signals inside the receiver. And finally, you can see the navigation solution. So this is where the experiment took place. They basically had set up 2 powerful jammers that you will see in a second. And they were transmitting different waveforms, at different powers and different tests, both for ground and for aerial vehicles. You see here the jamming to signal ratio, which can reach as high as 90 dBs. This is how we tested out our algorithms. We started driving. Just before they fired up the jammers, we were listening to the cellular LTE transmitter in the environment. We start mapping it in preparation to lose GPS. Then we have a period of GPS intermittency for about half a kilometer or 0.4 kilometers to be exact. And then we drove for about 3.5 kilometers completely in the dark. There is no GPS. I will show you shortly how the GPS IMU system behaved and how we were able to compensate for that by using signals from this tower. So all in all, at the end of the day, we were about 5 kilometers on a ground vehicle from that cellular LTE tower, and we were still getting good signals to help us navigate in the experiment. So this is what you are seeing here. This is the initial uncertainty around the tower. As you can see, it's pretty large. It's about 10 to the 6 in the sigma in both directions horizontally. So we start mapping the tower. You see the uncertainty ellipse, or the uncertainty ellipse shrinking, and it will continue shrinking as we move. So far we do have GPS. So you see here in white, this is the ground truth. This is from GNSS IMU system. Now, not all GNSS satellites were jammed, only GPS was jammed. So we were relying on other constellations to get the ground truth. In blue, you are seeing the radio SLAM solution, and you see it's pretty close to the ground truth, right? We are not using anything here except for cellular signals. We are not even using any IMUs there or map matching. So now they fired up the jammers. GPS is unavailable. This is, by the way, what our cell phones were showing when GPS was jammed. This blue halo, or the uncertainty, grew to more than 6 kilometers, and it started jumping around like it was possessed by the devil. It was pretty fascinating to see how a smartphone, just behaves when GPS is really jammed in the environment. So what you see here in red, this is the GPS IMU solution drifting. It kept drifting forever, really, as we moved. Whereas in blue, this is just with one tower. Just with one tower, we were still able to produce a very decent estimate of how we are moving. And of course, the idea, we can still listen to other towers outside of the jammed environment, but we wanted to see can we rely on towers within the jamming region, because the cellular infrastructure does depend on GPS for synchronization purposes. So this is the entire trajectory. You see how the red drifted away. This is the GPS IMU solution, whereas you can see here how closely we were. We were only 32 meters position RMSE, whereas the GPS IMU system was more than about 238 meters. So the next experiment I want to show you is how we can do this in not a GPS denied environment because someone is jamming GPS, but rather it is we are the GPS is denied So this was an experiment that we did what we are doing here is that you see here this rendering of the experiment. What we are doing is we are using cellular signals, just like I showed you before, coupled with a deep learning approach for multi-path navigation, which uses synthetic aperture navigation. So at a very, very high level, we are beamforming towards the line of sight, and we are nulling all the non-line of sight components that are coming from multi-path. And we are using deep learning approach for helping us do the synthetic aperture. You see us going up and down the stairs, and our solution is pretty much within 1 meter. We are also using an IMU which is not the velocity of the tape. So this is our system is basically used to IMU aided with and LTE signals, which are aided with this synthetic aperture navigation. As you can see, we are going deep into the building, and our solution all the way has been rounded to about 1 meter from the ground. And we got the ground truth by producing a map to a LiDAR system of the entire building. So that's us once again going up and down the stairs. At one point, we actually take the elevator, and probably you are experienced using your calls in the elevator. But nevertheless, the signals are still powerful enough for us to use in an elevator without the building. Okay, so let me now move real quick to navigation with LEO satellites. In a special issue of Inside Unmanned Systems, where we showed a simulation study of what is achievable with Starlink LEO satellites through on a UAV that is flying around this figure 8. So if we do have 44 LEO satellites with navigation frameworks, with differential navigation frameworks, sorry, I think I was not somehow, yeah, my connection dropped me, but maybe now you can hear me. So over over this 15-kilometer trajectory, we were able to produce a position RMSE of about 32.4 centimeters. But this is assuming that we can actually produce navigation observables from these Starlink satellites. So what I'm saying here is there is a lot of promise for what you can achieve with LEO satellites. The trick is, can you get something useful from their signals? Starlink, as we know, we do not necessarily know its signals, right? So how to do that? So to do this, we developed a cognitive opportunistic approach to decipher the signals we are getting from Starlink and produce a navigation solution from them. This work was featured in Science about a month ago, and later on in IEEE Spectrum. And in ION GNSS in September, we showcased the first ever positioning results with Starlink. You see here, those are results not only with Starlink, but also with previous work we had done on Iridium and Orbcomm to exploit their downlink signals. And our solution on a stationary antenna was only 6.5 meters from the ground truth. And you can see here how close we are. This was an antenna on the top of a parking structure. But obviously nothing is better than showing a mobile ground vehicle how we can do this on a real ground vehicle. So this video here will show you how we did this. So we equipped a ground vehicle with our with matrix, and the idea is to use one Starlink satellite, one Orcom satellite, and one Iridium satellite, and try to figure out how the vehicle is moving and aid the IMU on that vehicle with observables. I think there are some issues with the audio. Okay. Also, there are issues with the audio, so I will wait to watch the video and then watch and hopefully it's something down the way. Apologies for the audio issue. The music should not have been playing, but somehow it did. So what you saw there is us driving a vehicle and eventually being able to aid the IMU on the vehicle and traveling for 2 kilometers without GPS or without GNSS altogether by using signals from Starlink, from Orbcomm, and from Iridium. And you saw with a tactical grade IMU losing GPS or GNSS for 2 kilometers, the errors were more than 200 meters away, whereas we managed to bring this down to 38 meters. You may think, well, this is still a lot of error, but remember, we only used 3 satellites, and this is why we did the simulation study early on, which predicted if we do have 44 Starlink satellites, and this actually will be the case in the near future above us, where we can use their signals, we can bring this error down to meter level accuracy on ground vehicles and sub-meter level accuracy on UAVs. So with that, I would like to acknowledge the sponsors of this work: ONR, Air Force, NIST, NSF, Department of Transportation, and Sandia. And with that, I will give it back to Mackenzie.
Thank you all. That was great. At this time, we'd like to jump into our Q&A. So my first question I have is for Jonathan and Zach. How are the new technologies helping positioning in locations where satellite signals are not strong enough, such as indoor situations?
Yeah, so I'll speak, specifically to indoor situations, though, in outdoor, there's certainly GNSS augmenting systems, like different LEO constellations. But for indoor, there's a lot of interesting stuff with Wi-Fi or Bluetooth going on. Works, in a similar way using quadrilateration or, other techniques, just as it would with GPS satellites. But the downside to a lot of those is it requires a lot of upfront knowledge and, setting things up in the right places, because in having a knowledge of the environment in general, just to deal with multipath or deal with coverage issues. But certainly, that's one of the really interesting things to me is how those can be used to overcome unknown environments and doing it pretty quickly. So yeah, Wi-Fi and Bluetooth, I think, are probably the 2 big players right now. Zach?
Yeah, so those are the historically traditional players, but I would say don't forget about cellular signals in particular. So especially with 5G being rolled out and having lots and lots of towers around you and small cells, those will be even more attractive. So the video that I showed, unfortunately, maybe you didn't hear me narrate it. That was my student Ali walking in the building for about 15 minutes, 600 meters. And the position RMSE along the entire trajectory was less than a meter by listening to cellular signals. by listening to LTE signals in particular from 4 or 5 towers, something like that. And of course, we used an IMU, but without using the IMU, the performance didn't degrade by much. It was about 1 meter and 30 centimeters, 1.3, right? So those signals are very attractive. Now, there is a caveat, which is we need to know where the towers are beforehand, so we need to map them. But this is not a very difficult task if the people are really serious about using those signals. I would say I would prefer them personally over Wi-Fi because you can get more accuracy. And in some situations, like for emergency responders, and this was the motivation for our work, Wi-Fi may not even be there. Power in the building may not be there. And of course, Wi-Fi hotspots can be moved around, so there are no guarantee or less guarantees on how static they will be, whereas cell towers are less likely, and the database can be maintained more universally, not only for a building, but maybe for a metropolitan area.
Yeah, that's a good point. I think any signals of opportunity are really interesting, whether that's radio, 5G, television, who knows? I mean, there's a lot of signals out there. All right, I think next question.
Okay, thank you. This next question is for Mitch. What would be the best way of tackling a GNSS challenging environment such as rail?
Well, that's an interesting question for someone who spent 2.5 decades in aviation. But yeah, so it just so happens I dealt with folks in the rail industry and certainly within the Department of Transportation. Rail is a very challenging environment. Most people don't understand because you're not only dealing with wide open spaces, but you're dealing with urban canyons and multipath and tunnels and going across bridges that have metals surrounding you. So yeah, rail, and you also, in many parts of the country and certainly in almost all of Europe, you're dealing with vehicles that have high voltage connections sparking above your head. So yeah, looking at rail, certainly GNSS is one way. Certainly inertials have been there. Right now they use balance in the tracks to essentially measure their position. But those are expensive and they get very dirty and maintenance becomes an issue. Again, a systems of systems solution, in my perspective, is always the best one. And looking at all those things to support positive train control are going to be necessary. One size doesn't fit all in all situations. So I would say, certainly GNSS is going to be a great tool. But so are wheel counters and accelerometers and things like that. The biggest issue, of course, is parallel track spacing of 2 meters, and you need to know that trains are on different tracks and not the same track. So it's more challenging than most people understand. But I think that there are folks specifically working on solutions there. And again, a systems of systems approach would fit that as well as many other applications. I hope that answers the question.
Okay, this next question is for Zak. It's a two-part question. So the first part is, if PNT reliability is a real issue, why is the world then mainly focusing on vulnerable GNSS as the primary system?
Well, I'm not sure if I agree that the world is really only focusing on them. I think different communities and different industries, different stakeholders are focusing on different things, right? So if you talk to stakeholders for military operations, then their objectives are different than integrity, for example, is not necessarily one of the high up objectives as in, for example, FAA or Department of Transportation. You talk to consumer devices, then accuracy becomes probably their number one objective. So it really depends who you are talking to and what the objectives are. We are not there could be a silver bullet that answers everything, right? But maybe that silver bullet is more silver for some applications and less silver for another application, depending who wants what. But I wouldn't say that we are only focusing on one or the other. It really if you move around communities, which is what I tend to do, you will see different questions being asked depending on what are the challenges in that community.
Okay, and then the second part of that is what we miss is a solid cooperation between radio navigation researchers and large user groups. Where do you believe is that mutual understanding?
I think there is good understanding going on. Actually, it's a triangle. It's not only the research community and the user groups, but also the impact of government and setting the tone for what basically has to be pursued and what directions we have to go after. So, of course, the Institute of Navigation is a wonderful place for this exchange of ideas and having these discussions, which often lead to very exciting discoveries and shaping the industry. But also from the government point of view, there has been a push, very, very strong push recently for PNT resiliency and alternative PNT technologies, whether it's from NEST and their report that came out early this year, or the Volpe Center, Department of Transportation. And probably you are also aware about the executive order from the White House for PNT. Part of these efforts is also the Carmen University Transportation Center that we were awarded, which includes University of the Ohio State University, University of California, Irvine, UT Austin, and University of Cincinnati, where we are focusing. We have a large consortium that is really focusing on these particular issues of PNT resiliency and mitigation strategies.
Great. We have time for one more question. This one is for Jonathan and Mitch. Do you support GPS/GNSS spoofing capabilities in the form of standardized test suites or customizable test suites? Also, can you simultaneously jam or spoof multiple GNSS?
Yeah, so Orolia does offer the BroadSim product, whether it's BroadSim Solo or the standalone, and which, yeah, I mean, there's capabilities to inject multiple jamming and spoofing signals. So yes, and then in terms of, test suites, we do have, some suites that we've developed that we like to put our stuff through. We can throw the kitchen sink at it, but we like to kind of systematically look at different modalities and different threats so we can better understand the specific performance. And then, of course, sometimes we just throw everything at it just for fun to see how it does. And what was the second part of the question, Mackenzie?
Let me pull that up. One moment.
Sorry.
Oh, no, you're fine. The second part was, can you simultaneously jam or spoof multiple GNSS?
Oh, well, I guess, yes, then. Yeah, I mean, you can, it just depends if you're trying to do multiple constellations, it just takes, from a simulation standpoint, the different channels, and from an actual real world standpoint, you just need the different transmitters on the different waveforms.
You want me to take a crack as well, Mackenzie?
Sure, if you would like to.
Oh, sure. Okay. Well, so on the second part of the question, the good news is that we have worked very hard in international forums to make sure that GNSSs are compatible so that one receiver can use multiple constellations. Many people are working on dual frequency multi-constellation receivers now. So the answer is, yeah. The good news is we can use the same receiver for multiple constellations, and the bad news is you can use the same jammers and spoofers for multiple constellations to some extent. I won't call that an absolute. But the first part of the question, again, Mackenzie, could you repeat it?
Yes, that first part was, do you support GPS/GNSS spoofing capabilities in the form of standardized test suites or customizable test suites?
Yes, thank you. Yeah, so in fact, I would point folks, there's an IEEE standards committee that's been stood up, P 1952, specifically looking at PNT resilience. And I think that that's going to be a really important committee to look at the standards whereby you need to follow these standards to have a resilient PNT capability at the user end. I think, again, every user has different performance needs, but there's got to be a clear separation between, yes, I'm safe and secure, or no, I'm not safe or secure. And I can accept some level of economic impact, but I shouldn't accept any level of reduction in safety or security. And I think that the committee is going to have an interesting time defining what it means to be safe and secure. And I hope that what comes out of that will help guide people in terms of writing performance requirements for systems in the future. Over.
Great. All right. That wraps up our questions. Thank you all for sharing these insights with us today. That was very informative. We are now going to wrap up. I would like to thank everyone for attending. We appreciate your time. And once again, thank you for attending Measuring PNT Performance in Challenged Environments, brought to you by GPS World Magazine and our sponsor of the event, Orolia. If you have any additional questions for myself or for our speakers, you can reach out to us directly via the email addresses you see on this slide. A recording of this webinar will be emailed to you tomorrow and posted to gpsworld.com/webinars. Upcoming webinars from GPS World will also be posted to that page. Thank you all for attending, and we all hope you have a great webinar and the rest of your day.